Assalamu alaikum, my dear students. Welcome to the course Mathematical Physics 2, labeled as PHY 302. This course carries 3 credits, which means we will have 3 hours of lecture per week, and there are 100 marks, and you will have to get 50 marks to pass this course. You must have read the first part of this course, that is Mathematical Physics 1. The book we shall follow for Mathematical Physics 2 is the main textbook will be the book Mathematical Methods for Physicists by George Arfken. There are several editions available in our library. I will focus on the second or the third edition. The third edition is available online, and the second edition is available from the photocopy shop outside the department, which you can get from there. You will also get my notes from the same shop, and we will start from chapter number 8 of this book. Let me show you the third edition of this book. Well, these are my notes, which are available from the photo shop, and this is the book which I will load online. I will also load online my relevant notes for the particular lecture during each lecture, and you must possess all these notes and this book along with you, either online or the hard copy. You can get the hard copy from the bookshop, from the photo shop, and let us now start the chapter number 8. I will focus on my notes, which I have selected from the same book I have just mentioned, and this is the page from this book on chapter 8, and the topic is the differential equations. The main objective of the course you have already studied in the previous semester, and the course we will study in this semester on mathematical physics is in fact to train ourselves to solve differential equations and a few other topics. So you will be surprised to note that why differential equations are so important, that the entire course is focused on the solution of the differential equations. Well, this page will explain why differential equations are so important. It is the fact that whenever we take up any topic of physics and we apply physics on that topic, we will see that at the end we have a differential equations, particularly a partial differential equation of second order. So we cannot move ahead unless we solve that equation and then complete the topic of the physics. So that's why the differential equations are so important. And you can go through the text on these few pages before you, that is the partial differential equations of theoretical physics. So almost all the elementary and numerous advanced parts of theoretical physics are formulated in terms of differential equations, often partial differential equations. Among the most frequently encountered are these following equations. The equation first, number one, is the Laplace's equation, whose equation is del square psi is equal to 0. Well, you know that the operator del is a partial differentiator. So in fact this is a partial differential equation, and psi is the function which will represent any function of physics. So this is known as the Laplace's equation, and this equation is very common and very important equation which occurs in the studies of electromagnetic phenomena, including electrostatics, dielectrics, steady currents, and magnetostatics, and you know all these topics are from physics. B, the hydrodynamics, that is the irrotational flow of perfect fluid and surface waves, and then C, heat flow. D, gravitation. Number two is the Poisson's equation, which is del square psi is equal to minus rho over epsilon naught. The Laplace equation, which is the above equation, is in fact the homogeneous differential equation, because the right hand side is 0 and there is no source function. But if there is a source function, that appears on the right hand side of the equation, and this equation is known as the Poisson's equation. The Poisson's equation is a non-homogeneous with a source term minus rho over epsilon naught. Rho is the charge density and epsilon naught is the permittivity of free space. Number three, the wave Helmholtz equation and time independent differential equation. Now this equation is in fact the combination of the Laplace equation and the Poisson's equation, which shows that del square psi plus minus k square psi is equal to 0. So if you take this term on the right hand side, it becomes a non-homogeneous differential equation, and this is the most general equation, and we call it the Helmholtz equation. You can say that this single equation represents all the topics of the entire physics. So these equations appear in such diverse phenomena as elastic waves in solids, including vibrating strings, bars, membranes, sound or acoustics, electromagnetic waves, nuclear reactors. And then number 4 is the time-dependent diffusion equation, written here, del square psi is equal to 1 over a square partial derivative of psi with respect to time. So this equation includes not only the spatial derivatives, which is del square partial derivative, it also includes the partial derivative of the function with respect to the fourth coordinate, which is the time. Okay, I would suggest that you go through all these equations mentioned here and go through the text written, so that you can fully understand why the differential equations are so important in physics. So after establishing this fact, now let us move onwards to learn the techniques for solving the differential equations. Okay, my next topic is this one, separation of variables. Now, why separation of variables are required here? Because all these equations we have seen above you have seen that all these equations are partial differential equations of second order. Now, before we actually solve a differential equation, we need to convert this partial differential equation into ordinary differential equations. In partial differential equation, the function psi is a function of x, y, z in Cartesian coordinates, or it can be r, theta, phi in spherical coordinates. So you see that the function psi is an implicit function of all the variables. So that's why we write the partial derivatives. But we have to convert this into an ordinary differential equation. Ordinary differential equation, the derivative is written as d square psi over dx square. So we have to separate this implicit function psi. We have to split this function into three parts. The first part will be function of x only. The second part will be the function of theta on y only, and the third part will be the function of phi only. So we have to split this function. I will present the separation of variables using the polar coordinates, although over here you can see the separation in Cartesian coordinates, in cylindrical coordinates, and in polar coordinates. So let me jump to the separation of variables with respect to the polar coordinates. So this equation, k square will be a constant, and in fact if you change the value of k you will be scanning the entire physics. It is also written above that with various values of k, this Helmholtz equation will represent the equation in particular topic of the physics. So let me now jump to the, so that I can show that the separation of variables in spherical polar coordinates. So this is the separation of variables in cylindrical coordinates, and next will be the separation of variables in polar coordinates. Okay, in polar coordinates, this is the one page number 115 of the book, and you can see the Helmholtz equation written using the value of del square in polar coordinates, and the value of del square is 1 over r square sine theta bracket sine theta partial derivative with respect to the first polar coordinate r square partial derivative of psi with respect to r, and so on. And this term k square psi has been taken on the other side of this equation. So equation 2.83 has been written by using the value of del square in polar coordinates, and in the next step we will split this function psi, which is an implicit function of r, theta and phi, into a product of three functions: capital R, which is only a function of r, capital theta, which is only a function of theta, and phi, capital phi, which is only a function of phi. So that is the first step towards separation of variables, that we split the function, our implicit function, into explicit functions, product of three explicit functions: capital R, capital theta and capital phi. Okay, so in the next step what we have done here is we have rearranged this equation, equation 2.85 into 2.86. You can easily follow these steps over here. So we have put the function of y on one side and the function without phi and theta on the other side. So equation 2.86 relates a function of phi along to a function of r and theta above. Since r, theta and phi are independent variables, we equate each side of the equation 2.86 to a constant. Here a little consideration can simplify the later analysis. In almost all physical problems, phi will appear as an azimuth angle. This suggests a periodic solution rather than an experimental. With this in mind, let us use minus m square as the separation constant. Okay, you can follow the rest part of this separation of variables from this book, but let me see if I have done the detail of separation of variables in my notes. I think I have done it somewhere. Let me see. No. So you will have to go through these pages from the book to fully understand the separation of variables. Okay, so let me continue with my previous reading from the pages from the book. So what we have written, we have separated the variable phi, the phi part, which is in fact this part. For that purpose we have to multiply this equation with sine theta, let us focus on equation 2.86. Here we have separated the part phi, or we have placed the part phi on one side of the equation, and we have taken the rest part of the equation on the right hand side. So what do we conclude from the equation 2.86? Now if you look carefully, we have one side of this equation, that is the left hand side, depending only on the variable phi, and the right side of this equation you will not see phi anywhere. So the right hand side of this equation is independent of phi, whereas the left hand side has phi. So how can we equate these two terms? A term which is only a function of phi and a term which is not a function of phi. This can only be done if we assume that this part is equal to some constant, and of course the right hand side of this equation will also be part of that constant, and the constant we have put here is minus m square. So we have one equation 1 over phi d 2 phi capital phi over d phi square is equal to minus m square. So this is the phi equation. So now when we substitute the right hand side of this equation also equal to minus m square, and we come to the equation 2.88, and we separate the r and theta portion of this equation, then we end up with equation 2.88 and 2.89. If you look at the equation 2.88, this equation contains the variable r only, and the second term is the term containing the function of theta only, and we have done the same thing as we did for the phi part. So equation 2.89 has been written on one side of this equation the term containing r only, and the right hand side the term containing theta only. So again we have the same situation in which we have a side of the equation dependent on small r, and the right hand side of this equation not dependent on small r. So we will have to introduce another constant to write this part, the left hand side equal to that new constant, and the right hand side also equal to the new constant. So that is the result we get here. The new constant we have introduced, q. So we have separated the theta equation here as 2.90 and the r equation here as 2.91. Right. So we have achieved our target, that is, we have converted a partial differential equation into a set of three equations. The previous equation was the phi equation, and this is the theta equation, and this is the radial equation. So we have used the derivatives as d over d theta, or d over dr, or d over d phi, because now our function capital theta is only a function of theta, and capital R, which is only a function of small r, and similarly phi, which is only a function of phi. So equation 2.87, the set of these three equations, 2.87 and 2.90 and 2.91 was our target, and we have separated the partial differential equation into the set of three ordinary differential equations. Okay, if you want to see this, the more detail of this separation of variables, you will see it from my notes available from the Photoshop, the photocopy shop, or you can consult any book to see this. Okay, so the first step we have done is to convert the partial differential equation into an ordinary differential equation. Okay, so we have our differential equation. Any one of these differential equations can be written as y double dash, that is the second derivative of y, plus px into y dash, the first derivative of y, and this y will represent any physical function, as we have substituted phi, theta, or r, capital phi, capital theta, and capital r have now been written as small y. Okay, so that is the standard form. Equation 5.1 is the standard form of an ordinary differential equation of second order. So the separation of variables I have discussed here was with respect to the spherical polar coordinates, but I would also ask you to do this separation of variables in Cartesian coordinates and also in cylindrical coordinates, which is there in the above pages. You will see the separation of variables with respect to the Cartesian coordinates, with respect to the cylindrical coordinates also. Okay, so equation 5.1 you can say is the standard form of an ordinary differential equation of second order. Here px and qx are polynomials. Px is the polynomial as a coefficient with the first derivative. We have written the second derivative without any coefficient, only the coefficient of y double dash is just 1. So if you see anything associated with y double dash, you will have to divide this equation by that whatever is written along with y double dash to get this standard form. So in the standard form, y double dash must have a coefficient of 1 only, and whatever is then attached to y dash is known as the polynomial px, and whatever is associated with y is known as the polynomial qx. Okay, so every differential equation has a singular point. We will see a technique known as the Fravinia series method, in which we will expand this function into an infinite series about the point of expansion, which I will discuss later. But here you must understand that every differential equation has a singular point or ordinary point. Now, how this singular points and ordinary points are defined, it is done here, so you must listen carefully. If the function, the polynomial px and qx, remain finite at a particular value of x is equal to x naught, and this x naught is the point of expansion, x is equal to x naught will be an ordinary point. So if capital P and capital Q are finite, they are not infinite, both of them or any one of them, then this point x is equal to x naught will be called the ordinary point of the differential equation. However, if either capital P or capital Q are both diverge as x tends to x naught, then the point x naught is called a singular point. So this is the definition of the singular point of a differential equation. And then there are two types of singularities. One is the non-essential singular point. So we have seen that capital P and capital Q are both of them now tends to infinite as x tends to x naught, being singular point. So but if we multiply P with x minus x naught and we multiply Q with x minus x naught whole square, and now this term and this term becomes finite, although capital P and capital Q are individually infinite, but by multiplying capital P with this factor and capital Q with this factor, and it becomes finite, it would mean that we are having a non-essential singular point or regular singular point of the differential equation. So this is the definition of a regular singular point or non-essential singular point of a differential equation. Whereas the second type of singularity is the essential singular point, in which capital Px and capital Qx, they both diverge, but now this x minus x naught into Px and x minus x naught square into Qx still remain infinite. So even after multiplying with these factors, the terms remain infinite. Then we will say that x is equal to x naught is an irregular singular point or essential singularity. So you must go through these definitions here. So here we have discussed the role of the point of expansion x naught, which can be any point, any constant point. So x is equal to x naught, but sometimes we have to see the behavior of the differential equation, which we call the asymptotic behavior, and we have to see whether z naught now equal to infinity. So what is the role of this? What is the type of point z is equal to, z naught is equal to infinity? That is the asymptotic behavior of the differential equation. Because when we are dealing with functions, physical functions, for example the electrostatic potential due to a charge density at a point distant r from this distribution of charge, But if we take our point to infinity and we want to see what is the effect of this charge density at an infinite distance from the charge density, it means we are talking about z0 tending to infinity, and this is called the asymptotic behavior of the differential equation. So if we have a situation like this, that z0 tends to infinity, or the variable z is equal to infinity, then how can we check the type of point of expansion? So the only way is that we will introduce z equal to 1 over x. So we will substitute in our differential equation z is equal to 1 over x, and hence we will write the polynomial px now in terms of pz and the polynomial qx in terms of qz. So by substituting z is equal to 1 over x, and also we have to take the derivative. Now here is the derivative with respect to x, but we have to convert this to the derivative with respect to z. So we will substitute z is equal to 1 over x, and we go through these steps here to see how these derivatives are converted into the derivative with respect to z, and then get the value of p and q. So these are the new values of p in terms of z, and this is the value of q, new polynomial, in terms of z inverse, and you will see now you will see the role of this polynomial and this polynomial. And so I would suggest that you go through the steps written over here to understand the asymptotic role of the differential equation. Next, I have given an example to for example, this equation, x square y double dash plus xy dash plus x square minus n square y is equal to 0. You will later see that this equation is called the Bessel's differential equation, which is very, very common in our physical problems. So to see the points of expansion, normally we take the point of expansion x naught equal to 0, and the other is x naught is equal to infinity. So here I have discussed, so we have to divide this equation with respect to divide by x square, so that the coefficient of y double dash becomes 1, and when you divide this equation with respect to x square, you get the value of px as 1 over x and qx as 1 minus n square over x square. This is in fact the Bessel's differential equation of order n. N is some constant. So you will see in the following steps the discussion of the ordinary points and the singular points of this particular equation. So why we are studying this singular point and the ordinary points of a differential equation? It is important. We will see later that the nature of the point of expansion of a differential equation plays a very important role in determining the solution of the differential equation. Right. So I think I will stop here. So you should go through, because this was an introductory lecture. So in my next lecture I will start discussing the solution, and the technique we will introduce here is the most general technique of solving a homogeneous differential equation. So we will first apply this technique to the homogeneous differential equation, that is the differential equation on which the right hand side is 0, and we will learn this technique. So, and then we will move forward. Okay, so get the copy, your personal copy of my notes and the book from the photostat shop or you can rely on whatever I present here, whatever I have loaded here during my lecture, but it is advised that you must have the hard copy of my notes and the book. Okay, thank you very much. We will meet tomorrow to continue with our studies. So get yourself prepared, and you must possess whatever I have written here. Okay, thank you very much.